Hello.
So we're going to talk about the .NET 9 JIT and some of the new updates that are in there. Let me bring in your slides.
Sure.
There we go. Now, we've heard a lot about performance and some of the updates, and we heard from our friend Stephen Tobe about some of the updates that have happened. Feels like you're going to go deep on some of those topics.
We're gonna try. We can't get super deep in half an hour, but we'll do our best to sort of give you a flavor of what's going on, sort of under the hood, so to speak, in the .NET 9.
All right. Well,
So,
thank you so much, Andy. The stage is yours.
okay. So let me just sort of jump into things because again, we don't have a super long time frame. Every release, we try to make some pretty fundamental and important improvements in the ability of .NET to make your programs run more efficient. And you've heard a lot about things happening at sort of the library level, but in coordination with that, kind of down in the depths of the system, we also do a whole bunch of changes to just try to get the basic efficiency of programs running better. I'm going to go through a couple different areas here. I'm going to talk about some work that we did, or just to give you some background on exactly what the JIT is in case it's not clear or you need a refresher. Some things that we did about improving handling of just basic objects, and some exciting work that we're having done at 9 and that we're planning on building on in future releases. Some support that we've added now for ARM64, in particular, scalable vector extensions, which are now available in the new Cobalt 100 that Azure is hosting. Uh, Loops are an important part of every program, and we've made some big improvements in the ability of the JIT to optimize loops. We'll talk about those briefly. Some general things that sort of apply broadly across the board, and then just sort of wrap things up, and remind you of ways to get a hold of us if you see issues where you think we could be doing a better job or you want to congratulate us for already doing a good job. So the .NET JIT, we also sometimes call it the code gen, is a thing that translates your um, programs from assembly or from intermediate language, the thing that gets produced when you run a .NET build, into the actual machine code that the chip knows how to execute. Our code generator includes the ability to generate code for x64, x86, ARM, ARM64, and then also the community has added support for RISC-V and for LumaArch. So that means you can take your .NET program and run it on many different pieces of hardware. And each of those pieces of hardware often has many different variants inside of it of things that it can do. You might be familiar with a term like AVX512, which are the advanced vector extensions that Intel processors and AMD processors offer these days. ARM has similar sort of gradations, 8x and 9x features. And then also many different operating systems. These operating systems all have different conventions for the way that the machine code needs to operate in order to be compatible with the system. So we handle Windows, SysV, those most flavors of Unix, Mac OS, and so on and so forth. So there's a lot of different variations here, but there's sort of one engine behind all of this, and that's the .NET JIT. We usually compile methods one at a time, and the method is compiled to machine code just the very first time that you run it, hence the name just-in-time compilation. Turns out that same piece of technology also handles code generation if you're building your code ahead of time, like in native AOT or ready to run. So, terminology gets a bit fuzzy here, but basically we are generating the code that your application needs to actually run on the hardware that you want to run it on. And so in this talk, let's go through a sample of things that we've done in .NET 9 to make that process work better. Before I get started, I just want to remind people, in case you're curious, to look under the hood sometime and see what's going on. We've been trying to make it easier and easier to actually look at what the JIT does when it takes your program. There's a variety of ways you can do it. There's a very nice VS add-in plugin called Disasmo, where you can basically hover your mouse cursor over a piece of code that you've written and look at what the JIT would produce for that code. You can also get that information from command line processing, or there are some web interfaces where you can basically copy and paste your code into a website and look at the same thing. These are all pretty cool if you're ever curious to sort of know more or tinker around with your code and see how the expression of that code in assembly language changes. These are awesome things to know about. All right, so let's talk about objects, in particular about something called escape analysis. So you probably know in the world of .NET, there's roughly two kinds of data types. There are ref types and there are value types, or sometimes we would call those objects and structs. And ref types are classes and structs. And ref types are things that are allocated always on the GC heap historically. Their lifetime is determined by the GC, and that's one of the big values that the GC brings. Like you can create an object, you don't have to do anything explicit to deal with the fact that the object is eventually going to become interesting and that that storage can be reclaimed and reused for something else. The GC figures it all out for you. Um, and then there are structs or value types. These are usually allocated on the stack, but you can box them and put them on heap if you really want them there, or sometimes inadvertently they'll get boxed when you weren't expecting it. If they're allocated on the stack, then a bunch of good things happen. The fields of that value type can be promoted to the JIT and act as if they were effectively local variables in your method. And those promoted fields can live in registers, they can be aggressively analyzed and optimized. And so a lot of good things happen when promotion kicks in for a struct. And the lifetime of the struct is determined by the lifetime of the stack frame where the struct is allocated. So when that particular stack frame returns, that storage is freed up and it can be reused. So you get somewhat cheaper allocation, one might say. It's not slam dunk, but likely cheaper. If you end up copying your struct to the heap via boxing, then the lifetime, just as with a class, is going to be determined by the GC. And when you want to operate on the thing, typically you have to unbox it, copy it to a local stack allocated case, use that in your computation. So what we've done in .NET 9 is we've enabled a new technology in the JIT called object stack allocation, where if we can prove that even though you created an object and you said to put it on the heap, if the lifetime of that object is bounded, constrained by that stack frame that allocated it, then we'll treat that object like a value type, like a struct. And so we'll allocate the storage for the object on the stack. And then we will, all those good things that happen when you have a struct kick in, we can promote the fields, we can aggressively optimize the fields. This will work even if you have a boxed value type. And the key enabler is this proof that the lifetime is constrained, and that's the thing we call escape analysis. If you're familiar with Java or Go, they have had this capability for a long time. In the case of Java, they don't have structs, so having escape analysis and stack allocation turned out to be key to doing a lot of things. The upshot is when this kicks in, you have less heap allocation and better code optimization at the same time. So it's a really nice combination. There's a simple example, hopefully simple. We have a struct here, or actually we have a class here called a rectangle. It implements a shape interface. And we're just going to create one of these guys and we're going to call a method on it. So pretty straightforward. But when we create it, we're going to refer to it through its interface type rather than through its class type. And when we do that, then the runtime has to assume generally that this interface could be implemented by a bunch of other classes. And so when we generate code for it, we have a bunch of possibilities. Now in 8.0, we were smart enough to see that this thing was really a rectangle under the covers. So we basically devirtualized that interface call. But in order to make interface dispatch work, we had to allocate an object. And so we're still allocating an object in 8.0. And then we're initializing its field. So if you sort of look at that little box of CodeGen that says 8.0, you'll see there's a call in there to a method call or a routine called core info new help new s fast. That's allocating a heap object. We then fill in the fields of the heap object, writing 2s and 3s, and then we read those back to compute the area. So we immediately read back the values that we just wrote, and then we return. Now that object that we just allocated can't be referred to anymore, and so it's going to eventually be collected by the GC. But you can see we went through a lot of work to create an object that we didn't use for very long, and that just seems kind of unnecessary. On .NET 9, we're able to prove that that object cannot live longer than the method that it's allocated in, so we no longer need to allocate the object. We promote its fields very aggressively, and so we're able to see that instead of writing 2 and 3 to memory, we can just keep them in registers. And then we see the way that those are used, and we understand that the values are just immediately consumed by this multiplication. We propagate those constants to the multiply, and we figure out what the answer is. So in .NET 9, we just return the number 6. There's no object, there's no fields, there's no computation. Everything is nicely cleaned up. All right, so let's switch gears a little bit and talk about ARM64. As you know, Microsoft has just introduced its own first captive ARM64 host in Azure called the Cobalt 100. Offers very awesome computing power. I think also very attractive pricing, something everybody ought to really be thinking about for their cloud workloads. One of the nice things that this machine offers is something called scalable vector extensions. And I'm going to just give you just a very brief taste of what this means. when you have vector processing, you're able to do things, in basically in chunks, in vector sized chunks. So let's imagine that we're trying to add up, an array here, and say our array has got 10 elements in it. If I have a vector of size 4, I can do 2 adds of 8, and then I can do 1 add of 2, and then I can accumulate. But that 1 add of 2 is not vector sized, and so you'll see in the circle there, instead of me being able to do just vector operations, I have to drop back for this little tail of processing, these last few elements, to scalar processing and sort of add them up one by one. And so you find very commonly in these machines with vectorized code that you end up writing a lot of this little residual loop code. People call it tail loops, for example. In SVE, there's a very nice feature. It's also available in AVX 512 on Intel, where you can actually add predicated operations into your vector operations. And so one of the benefits is you can eliminate the need for these tail loops entirely. So what happens is, in this case, we do 2 vector operations, both of length 4. We also produce a mask at each step saying which elements of the vector are active. When we get to that last step, the mask basically turns off 2 of the elements of the vector. And so instead of doing a size 4 add, we end up doing a size 2 add. So in 3 steps, we've managed to add up all the numbers. We have to do one more reduction at the end to add the 4 vector lanes together. And voila, we have our answer without any extra fussing around with a tail loop or anything like that. So you can really get some nice benefit out of these predicated or masked operations in your vector processing. Obviously, you got to do some manual coding here to take advantage of it, but it's something that if you're interested in really high performance vector code, it's worth checking out. And so in .NET 9, we've added support for 281 new APIs for SVE, including all those categories you see there, a whole bunch of actual instructions that we can emit. This is all hooked up to vector of T. So it's going to act like we have scalable vectors. It turns out in this implementation, we're going to hard code the vector length to 16 bytes. But in the future, when we get onto hardware that has longer vector support in hardware, we're going to have that value be able to adjust upwards. One is a cool thing to check out. We'd love to get feedback on this and see how well our implementation works in practice on code that you might want to vectorize. Let's switch topics again and talk a little bit about loops. These are things that if you're familiar with compiler technology, you probably thought that we were already doing inside of our code generator. Turns out that we weren't. Basically, one of the key things about loops is to understand so-called induction variables. And induction variables are values within the loop that change predictably from one iteration to the next. Let's look at this simple loop here on the left. We have a value here, I, and I is simply incrementing by 1 every single loop iteration, right? So we're able to do the analysis now to understand quite a bit about how the value of I evolves as the loop processes. And in this particular case, we're going to take advantage of that. We're going to realize that inside the loop, you're not actually making any reference to I at all. The value of I isn't used anywhere. It's only used to control the loop. And because of that, it's actually more efficient for us to re-express the loop as counting downwards instead of counting upwards. So instead of effectively writing for I equals 1 to I equals 1, I less than n, we change it to be if I is equal to n, and we go downwards until we get to 0 or n minus 1. So anyway, so we end up effectively doing this transformation that you see over here on the side. Now you might wonder, like, well, what's the point of that? Why do you even bother? If you look at the code that's in purple, obviously this is machine code and not all of you may be comfortable with it, but you can notice one thing is that on the left we had 4 instructions and on the right we have 3. So hey, we got rid of 1 instruction in the loop. It should run a little faster. The other thing that's actually a bigger deal is that the version on the left is using 2 registers. It's using a register to remember what the value of I is, and it has another register to remember what the value of n is, where the code on the right only needs to keep track of one thing. And so we've freed up a register that could be super useful somewhere else in the loop. Say we had an actual interesting computation going on here. So we get a smaller loop. It uses fewer registers. It's just better overall. Similar kind of thing we can do now that we can analyze induction variables is strength reduction. So now you have some sort of operation in your loop. Typically, it involves a multiply. So there on the left, you can see we have I controlling the loop. Now we do have a reference to I inside the loop. But when we use it, we're always multiplying it by 3. And multiplication on most computers is not as cheap as addition. And so if we could somehow re-express that multiplication as an addition, we might be able to make the loop run faster, save some time, And this is what we can do when we have strength reduction. So in this case, we understand that while I is incrementing by 1 every iteration, I times 3 is incrementing by 3 every iteration, right? And then we also understand again how the value of I is evolving. We turn this into a down counted loop, okay? And we replace the multiplication in there by an addition. So if you look at that transformation, then you might have to squint a little to convince yourself that we're actually doing things correctly. But now we have a down counted loop, so we're using potentially a fewer less registers for that. And also we've gotten rid of the multiply, changed it into an addition. So again, the loop is now operating more efficiently. Um, and as a final piece, this one might be a little bit hard for people to understand, but let's give it a try. Um, there's a mode in ARM64 called post-increment addressing mode. So if you are walking through a data structure like an array, effectively somewhere in there, there has to be a pointer that's advancing along, pointing at each element of the array. Um, and in .NET 8, we would actually compute that pointer value on the fly by taking I and multiplying it by the size of the array element and adding it to that base element of the array to figure out where to point. And that's what that very first instruction in purple there on in the middle column is showing, is basically adding the result of that thing. And then that addition happens sort of just for the array access. And then we have to increment I, and we have to do the computation in the loop, which is adding up the sum. So you'll see that there's effectively 3 additions going on in that loop, one of which is just sort of used transiently to compute the element address. So if you could capture that and you could do the addition and take advantage of the fact that it's incrementing, effectively the loop control thing, you can eliminate an addition, and there we have it on .NET 9. There's one less addition happening. And the addition that was explicit in the addressing mode before is now in blue, has a special syntax, which basically means we're going to use x0 as the address of the element, and then we're going to increment x0 by 4. So there's an add hidden in there. So again, fewer registers, fewer instructions, faster processing, all good stuff. All right, let's talk a little bit about some general optimizations. So as you know, in .NET 8, we introduced dynamic PGO. In .NET 9, we've made some enhancements to dynamic PGO. I'd like to just touch on one of those here. And then we've also made some improvements to inlining. So in .NET 8, most of the activity around PGO had to do with virtual calls and interface calls. So we would profile, look at what types were involved in those, and try to make those operations be more efficient by guessing or predicting what the outcomes might be. And so in .NET 9, we've extended that to include some other operations that deal with types like casting. So in this case, we have a simple question like, we're just going to look at an object and say, hey, is this object implement iCollection, right? So you might think, well, okay, that seems like a fairly simple thing to do. But when you actually look at the code that .NET 8 generated for that, the code for this is collection, it has to delegate the heavy lifting off to this helper method. And the helper method, I don't have the code here for it, but turns out it actually does a fair amount of analysis, because implementation of interfaces can go through some twisty paths. And so there's a lot of checking that goes on here. And so, potentially it takes a while. Now, what we did in .NET 9 is, when we run this version at tier 0, we sort of watch what types you present to this interface call, or this helper call. We're like, are you asking about the same type a lot? And if so, maybe we can sort of guess that might be the type that you ask about here, and bypass all of this and figure out what the answer is up front. And indeed, that's what we've actually done in .NET 9. So here's the same code. You'll notice that if you look at the code gen on the right, at the very bottom, you still see sometimes we have to fall back to that general helper and be like, hey, we couldn't figure it out. We got to go do the general thing. But before we get to that point, we do a couple of quick checks. We're like, okay, is the object that you passed us not null? And if so, is it this specific class that we saw you asking about a lot before? And if the answer to that is yes, then we actually know the answer, and we sort of just quickly compute it and we're done. So this is another kind of profile guided optimization, where by observing how your code behaves, we can try to anticipate when we go to generate optimized code that it's still going to behave that way, and provide these fast paths and speed things up. Now you might think this can't be that big of a deal. Like, how much difference is this going to make? So here's some little benchmarks that we ran. These sometimes are kind of misleading because we're really focusing here on some of the overhead involved in doing these casts instead of, there's not a lot of computation once you get the answer, but still, these are things that you might end up doing in your code or that your program might doing. So if you look at the benchmark.net results over there on the right, you can see that, these things went something like a factor of 2, factor of, 6, factor of something faster because of these changes. So it actually speeds things up quite a bit in general. All right, and then one last thing. So one of the big powerful features in .NET are generic types and generic methods. And there's a fair amount of machinery under the cover to implement these things and implement them efficiently. And we're always looking for ways to get in there and actually make that stuff work even better. Now, one of the things you may have seen in the past, or maybe you haven't seen it, but is that when you have, say, 2 different generic methods, like here we have 2 different generic methods called test and callee, that when one of them calls another, sometimes there was actually a bunch of extra computation that had to go on because we couldn't effectively combine them together via inlining. So if you look at .NET 8 here we have test calling callee. It looks like sort of the same thing is going on, like there's a T in all of these. It turns out when we generate code for test, and it's calling callee, we don't necessarily know right ahead of time that callee is going to get the same type that test has. It may seem weird, but that's actually the way it is. So when we go to call callee, we got to go do a bunch of work and figure out, like, hey, like, what type is callee actually going to be instantiated on here? And that code in the box where it says runtime lookup is actually going off and doing this thing. And not only do you see like a bunch of checking, you see yet again another helper in there. Like, wait a minute, like we got to go and ask, go to some other piece of code and figure this thing out. So potentially kind of inefficient. And then when we actually go to invoke the callee, we can't inline the code. We have to call it. So down there at the bottom in that thin skinny box, we're actually calling this method. And if we invoke it on something like string, that'll turn out that string is a reference type. So type of t.isValue type is going to be false. So we're doing all of this work basically to discover something that maybe should have been obvious to us, that the answer was indeed like false. Anyway, so when we get to .NET 9, then the end and we managed to remove all those bottlenecks about inlining from one shared generic method into another. And once we do that, we know in this case that whenever we have a shared generic, the type that it's being shared over is always a reference type. So it's never a value type. And so all this method does in .NET 9 is simply immediately return false. So again, you can see, big difference in performance between doing this kind of stuff to discover that the answer is false and basically doing this kind of thing to know that the answer is false. And I had a chart on here. I think I must have lost that version. But anyways, this box here down at the bottom is showing what our benchmark system told us this change made in our code. You can see many benchmarks improved. You're probably going to see some improvement in your own code if you do this kind of thing fairly frequently. So the upshot is, with this optimization, generics basically compose better with each other. They play along nicely. You can use them without worrying about the fact that when you cross from one generic method to another, or from one generic class to methods of another generic class, that potentially you're losing a little bit of performance because of these things. All right, so let's wrap things up. So I've shown you in the past 20 minutes or so a small sample of the changes that we made in .NET 9. It turned out we made about 1,100 changes to the JIT over the year between .NET 8 and .NET 9. Clearly, there's no way I could even bother to, give you a view of more than a very small fraction of them. I tried to just highlight a few things that we thought were interesting. And the good news is the only thing you really need to do to see the benefit of all this work is update to .NET 9. You don't have to change anything about the way you code or deploy or anything like that. You might be curious to try your code on a different platform, like, hey, maybe I should run on ARM64 instead of on Intel or whatever. But you know, you can just pick up the new release and immediately you get these benefits without changing your code at all. Um, and we would love to hear your feedback if you see things when you do this where performance isn't what you expect, or if performance is good. We always love to hear feedback. We're especially interested if you are going to try out ARM64 and the Cobalt 100, and try these new experimental SVE extensions that we talked about. So if you try to vectorize your code in ARM64, you're taking advantage of the predication, all of that. Please let us know how it goes. Um, And here are our various links for some things that you can try. So, one good way to get a hold of us is actually to open up issues on the .NET Runtime GitHub repo. We're super responsive. We generally are, quite active, looking for feedback and problems that people report or anything like that, or suggestions on how we can do things better. I mentioned SharpLab. That's the online web viewer. That you can try and look at your code. We did a blog post talking about the engineering of the SVE extensions that might be of interest to you. Um, Disasmo, the plugin that I showed, the VS plugin to look at the code. And then a couple issues you might want to look at in our GitHub. One is a discussion of some enhancements to the object stack allocation phase that I talked about earlier. And another is our proposed work for .NET 10. Anyways, so feel free to check those things out. Again, get a hold of us if you have any questions. And with that, I want to thank you very much for listening in.